Hello, chemistry students, and welcome to Chapter 10, Section 1 on the mole, a measurement of matter. So as we look at the mole in terms of how we measure matter, we have to remember that chemistry is a quantitative science. And this means that you will analyze matter and then perform calculations that relate to the different compounds in a chemical reaction. That's what quantitative means. It means you can measure something. To solve these problems, you will need to be able to convert different units. And this is probably kind of the trickiest part of chemistry that many students kind of have problems with. So we're going to kind of go from really, really simple and work our way slowly through this. So finding a mass from a count. A sample problem question. What if the mass of 90 average-sized what is the mass of 90 average-sized apples if 1 dozen apples has a mass of 2 kilograms? So we have some information here and we're going to solve. We'll first list the knowns and the unknowns. So we'll use dimensional analysis to convert the number of apples to the mass of apples. We know that the number of apples is 90 and that 12 apples is equal to 1 dozen apples, and that 1 dozen apples is equal to 2 kilograms of apples. And we're supposed to find the mass of 90 apples in kilograms. We'll solve for the unknown by identifying the sequence of conversions needed to perform the calculations. The number of apples, we have to convert that to dozens of apples, and then we have to convert that to the mass of apples. So we'll write the conversion factor to convert from the number of apples to dozens of apples. We know that 1 dozen apples is equal to 12 apples, so that is our conversion factor. And then we write the conversion factor to convert from dozens of apples to the mass of apples. And we know that 2 kilograms of apples is equal to 1 dozen apples. Then we'll solve for the unknown by multiplying the number of apples by these 2 conversion factors to get the answer in kilograms. And we have to set up our problem so that our conversion factors will cancel out the labels. So we'll take our known 90 apples and then multiply by our 2 conversion factors. 1 dozen apples for 12 apples, and 2 kilograms of apples equals 1 dozen apples. And we have to set up, in terms of numerator and denominator, so that we can always cross off labels from top and bottom. So if we have a numerator apples, that will eliminate the denominator apples on the bottom. 1 dozen apples on the numerator can be eliminated by the 1 dozen apples on the next denominator. So what we're really doing is taking 90 times 1 times 2 and dividing it by 12 to get 15 kilograms of apples is the mass of 90 apples. The units apply, apples and dozen apples will cancel, so the answer has the unit kilograms because we want to cross off everything that we don't need to be left with a label that we do want. Does the result make sense? A dozen of apples has a mass of about 2 kilograms. If we have 90 apples, it's less than 10 dozen apples, so the mass should be less than 20 kilograms of apples because 10 dozens times 2 kilograms per dozen equals 20. What is a mole then? So this is where we get into chemistry and how we use chemistry and moles to determine the matter. Recall that matter is composed of atoms, molecules, and ions. These particles are much, 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 much smaller than even grains of sand, so there will be large numbers of them in even a small sample of a substance. This is about counting eggs. It's easier when the eggs are grouped into dozens. So we know that 1 dozen is equal to 12 of things. And that basically is what a mole is. So if we count with moles, chemists use the unit called the mole. And a mole, abbreviated MOL, of a substance is equal to 6.022 times 10 to the 23rd representative particles of that substance. And a mole is the SI, a standardized unit for measuring the amount of a substance. The number of representative particles is a mole, 6.022 times 10 to the 22nd, and that is called Avogadro's number. The term representative particle refers to the species present in a substance, usually in the form of atoms, molecules, or formula units, and the representative particle of most elements is the atom. 7 elements normally exist as diatomic molecules, like H2, N2, O2, F2, Cl2, bromine, and iodine. And the representative particle of these elements and of all molecular compounds is the actual molecule. The molecular compounds water and sulfur dioxide are composed of H2O and SO2 molecules, respectively. And for ionic compounds, such as calcium chloride, the representative particle is the formula unit calcium chloride, CaCl2. So to convert between the number of particles and moles, this relationship for 1 mole is equal to 6.022 times 10 to the 23rd. Representative particles will be the basis for the following conversion factors that you can use to convert the number of representative particles to moles, and from moles to the number of representative particles. So this is the conversion factor, which will be incredibly important for you to use. 1 mole is equal to 6.022 times 10 to the 23rd representative particles. And we can turn it around opposite. 6.022 times 10 to the 23rd on the top is equal to 1 mole. So we can flip it around and use that conversion factor depending on when we're multiplying to make sure that units will cancel out. So let's do a sample problem, converting the number of atoms to moles. Magnesium is a light metal used in the manufacture of aircraft, automobile wheels, and tools. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? We'll list the knowns and the unknowns, and we first start with the desired conversion here, that we want to go from atoms to moles. We know the number of atoms, that they give us 1.25 times 10 to the 23rd atoms of magnesium, and the unknowns are the number of moles. So we want to go from atoms of magnesium to moles of magnesium. We'll solve for the unknown first by stating the relationship between moles and the number of representative particles, and we have that already. We know that 1 mole of magnesium is equal to 6.022 times 10 to the 23rd atoms of magnesium. With the conversion factors, you get based in this relationship. We'll take the conversion factors, either taking the Avogadro's number on the bottom or the top, and we'll take the one on the top with the Avogadro's number on the bottom in order for our units to cancel out. So let's set up our problem. We have 1.25 times 10 to the 23rd atoms of magnesium, and we're going to take the conversion factor, which puts Avogadro's number on the bottom because we want to make sure atoms of magnesium cancels out. And then we're left with moles. So we're basically taking 1.25 times 10 to the 23rd, dividing it by 6.022 times 10 to the 23rd. 10 to the 23rd is the same number, so we can cancel out those 10 to the 23rds. So we're really just dividing 1.25 divided by 6.022 to get 0.208 moles of magnesium. Significant figures is 3, so we're just going to be left with 3 units after the decimal. Does the result make sense? So the given number of atoms, 1.25 times 10 to the 23rd, is a little less than 1/4 of Avogadro's number. So the answer should be less than 1/4, 0.25 moles of atoms, and the answer does have significant figures. Suppose you want to determine how many atoms are in a mole of a compound, and to do this, you must know how many atoms are in a representative particle of the compound, and this number is determined, and you can get it from the chemical formula. So the number of marbles, for example, in a dozen cups is 6 times 12, or 72 marbles. Similarly, a mole of molecules contains more than a mole of atoms. So to find the number of atoms in a given number of moles of a compound, you must first determine the number of representative particles. And to convert the number of moles of a compound to the number of representative particles, like molecules or formula units, multiply the number of moles by 6.02 times 10 to the 23rd representative particles divided by 1 mole, and then multiply the number of representative particles by the number of atoms in each molecule or formula unit. So converting moles to the number of atoms. Propane is a gas used for cooking and heating. How many atoms are in 2.212 moles of propane? But propane has this chemical formula, C3H8. So we have to take into account the number of atoms there that we're dealing with. The desired conversion is from moles to molecules to atoms. We know the number of moles, 2.12 moles of propane. We know that 1 mole of propane, because that's the one unit, is equal to 6.022 times 10 to the 23rd molecules of protein. And 1 molecule of propane is equal to 11 atoms. How did we get that? Well, we just count up the number of atoms. We have 3 carbons and 8 hydrogens. So 8, 9, 10, 11, we get 11 atoms. And then the unknowns that we're trying to get to, the unknowns will be the number of atoms. So let's set up our problem. Write the conversion factors to convert from moles to molecules. And remember to write the conversion factors so that the unit in the denominator will cancel the unit in the numerator of the previous factor. So we'll solve now. We'll take 11 atoms is in 1 molecule of propane. There are 3 atoms of carbon and 8 atoms of hydrogen. That's how we get 11 atoms. Write the conversion factors you get based in this relationship. So we start with what they give us, 2.12 moles of propane, multiply by our conversion factor using Avogadro's number, 6.022 times 10 to the 23rd molecules of propane for 1 mole of propane, because then our moles of propane can cancel out. And then we're going to use how many atoms in each molecule of propane, because then molecules of protein will cancel out and we'll be left with just atoms, which is what we're trying to get. So we'll multiply across the board and we get 1.4 times 10 to the 23rd atoms in 2.12 moles of propane. Does the result make sense? So there's 11 atoms in each molecule of propane and more than 2 moles of protein. So the answer should be more than 20 times Avogadro's number of the protein molecules. And the answer has 3 significant figures based on the 3 significant figures in the given measurement. Molar mass then, so the mass of a mole of an element. The atomic mass of an element expressed in grams is the mass of a mole of the element. And the mass of a mole of an element is its molar mass. So for example, carbon is equal to 12.01 grams per mole. That's the molar mass. Hydrogen is 1.008 grams per mole. That is the molar mass of hydrogen. How many atoms are contained in the molar mass of an element? So the molar mass of an element contains 1 mole, or 6.022 times 10 to the 23rd atoms of that element. And the mole can now be further defined as the amount of substance that contains the same number of representative particles as the number of atoms in 12 grams of carbon-12, for example. So the mass of a mole of a compound, you count the atoms in the compound, you look up the mass of each element on the periodic table in the compound, and then you can multiply the mass of the element by the number of atoms of each element and then add up the total mass. So let's find the molar mass of a compound. The decomposition of hydrogen peroxide, H2O2, provides sufficient energy to launch a rocket. What is the molar mass of hydrogen peroxide? So using the periodic table, the masses of the elements and the number of each element to calculate the molar mass. So we know the molecular formula is H2O2. From the periodic table, we know that the mass of 1 mole of hydrogen is equal to 1.008 grams per mole of hydrogen, and the mass of 1 mole of oxygen is equal to 16 grams per mole of oxygen. And the unknown, which is what we're trying to find out, is the molar mass in grams per mole. So multiply the number of each element, moles, by the mass of each element, and then add up the total. So H2O2, we have 2 hydrogens, so we take 2 times 1.008 plus 2 oxygens times 16. So we get a total of 34.016 grams per mole. Does the result make sense? The answer is the sum of the 2 times the molar mass of hydrogen and oxygen, which is about 34. Never round your molar mass. You should write down all of the digits off of the periodic table and do not round your final answer at all. All right, thanks for listening, guys. We'll see you for the next section, and God bless your studies this week.